Thank you so much to your organizers for the invitation. It's really, really nice to meet in person and see so many friends in one place. Yeah, being the first speaker at a conference, I put some pressure on me, but I'll try to do my best. And I'll try to go very slow, so please stop me and ask me questions. Okay, so I plan to talk about mean field approximations for high-dimensional regression today. This is based on a set of works with Sumit Mukherjee, who's at Columbia, and Jiaze Qiu, who is currently a fourth-year PhD student here at Columbia. So the theme of this workshop, as David mentioned, is graphical models, statistical inference, and algorithms. So this particular talk will prominently touch upon the first two themes. So we talk a lot about statistical inference, and we talk about ideas of graphical models that can be useful in that context. And in particular, we talk a lot about Bayesian, right? So the talk, to me, at least in my mind, is sort of in three parts. The first part is relatively short, where we'll just introduce the notion of variational inference in the context of high-dimensional Bayesian posteriors. The second part will be about high-dimensional generalized linear models. And then the third part will be about linear models, but in a particular specific scaling. Okay, so with that, let me jump right in. So this is just a gentle reminder for the basic structure of Bayesian inference. I think this is familiar to everyone here, but this will help us set up some notation, right? So at a high level, Bayesian inference sort of proceeds as follows. We see some data D. We put some class of parametric distributions, P theta. We assume that the data is we fit one of these parametric models to the data. We put some prior on the parameter space, construct our posterior, and then in Bayesian inference, our inference is based on the constructed posterior distribution. Right? And from a statistical perspective, there are two main questions, right, that we have to wrestle with. The first is, what are the properties of this posterior distribution? In this context, what we are generally thinking about is the fact that when we have this parametric class of distributions, typically in modern applications, P is quite large. So we are thinking about a posterior distribution in sort of quite high-dimensional space. So we are interested in understanding, what are the properties of this probability distribution in high dimensions. Right? That's sort of the main motivation. Intricately associated with this statistical question is a computational question, which is, okay, we have this high-dimensional posterior distribution that we want to work with. How do I approximate this distribution? And when I say approximate, I kind of mean it in a loose sense. For example, you could think about sampling from this distribution. You could think about approximating integrals under this distribution, and so on. So these are essentially the two main questions that are of interest in this set. Now, to answer the second question, which is, how do we approximate integrals, or how do we approximate the sample from the posterior distribution? The traditional answer has been to rely on Markov chain-based methods, right? So typically, we try to come up with some Markov chain algorithm that will run sufficiently long, give us an approximate sample from the distribution of interest, and then we can work with that. And there is of course a very long and rich line of work related to Markov chains for such models. However, proving theoretical guarantees for these MCMC algorithms can still be challenging for many learning problems. So an alternate perspective that has emerged in statistics, probability, and machine learning, I feel, over the past 2 decades, has been this idea of variational approximations. I think in statistical physics, this idea goes way back. So the idea in this case is, okay, what we'll do is that we have this intractable distribution. Maybe it's difficult to directly work with it. What I will do is that I will instead approximate this distribution, usually in a KL sense, from using distributions from a more tractable family. That's just the idea. One of the reasons why this is quite attractive is that it converts this problem of approximating a distribution or sampling from it to a problem of optimization, although an optimization now over the space of probability distributions. And in particular, if this class C on which we do our optimization is simple enough, then often this optimization is quite tractable, it's very fast, and in practice seems to work really well. So typically the simplest class of distributions that one can think about is the class of product distributions. So C will be the class of product distributions, and we can try to approximate our distribution of interest in terms of a product. Right? So one way to intuitively think about it is that we have some high dimensional distribution. If the dependencies among the coordinates are sort of relatively weak, if there is no strong long-range correlation, maybe I can throw away the correlations, kind of get a product distribution, and maybe it will be a reasonably good proxy for the distribution of interest. Right? So this strategy where we use this family of product measures to approximate posterior, this is often referred to as naive mean field approximation. And this is used quite a lot in problems such as topic modeling and so on. While this has been used a lot in practice from computational considerations, what I hope to convince you of today is that it can also provide a very interesting theoretical device to analyze distributions of interest and to understand the problems. Right? That's how I'll be using this idea of naive approximation. Okay. So before I go on, maybe I'll pause for a second to see if there are any questions regarding variational approximations or the naive mean field strategy. Yes.
So X is some realization of D?
Yes, sorry. Yeah, there's some notational conflict here. Yes. So X by X, I mean, it's a generic notation for the data. Okay, great. Now, naturally, as we have already kind of alluded to, of course, we don't expect this strategy to be, always accurate, right? If the coordinates in my distribution are kind of very heavily dependent, then this is probably not going to be a very good strategy, right? So the question somehow is, when is this a reasonable thing? And what I'll do, so this is sort of where we jump on to the second part of the talk today. So I'll talk about the utility of these ideas in the context of high-dimensional generalized linear models. So this is based on some ongoing work with Sumit Mukherjee and Jiaze Qiu. We have the results. I hope the paper will be on right soon. Okay, so what is our setup? So we work with a so-called canonical GLF. So the idea is that I have n data points. Yi represents my response. So if you want to think of a concrete model, think of a logistic regression kind of setting where Yi is 0 or 1. Xi's are my features. These are p-dimensional. So we typically, will stack them. Bold Y will refer to the vector of responses. Bold X is the data matrix where every row represents one of the feature vectors that I have from data points. And for simplicity, for the moment, throughout this talk, okay, for this part of the talk, I'll just work under very simple product drivers. Right? So the Bayesian model that I fit to the data is that, I imagine that my coordinates are IID from some prior pi, and then my log likelihood. So this little L, it basically represents my log likelihood for the model. It necessarily, for a canonical GLM has this form, right? So this function B is the cumulant generating function for the model. For logistic regression, it has an explicit form. And throughout our analysis, we'll assume that this function B and its derivatives are nice. One other technical assumption that I'll make for the moment, I think this is at the moment a restriction coming from our proof strategy necessary. So I'll be assuming that my prior is supported on a bounded set. Right? As long as I make that assumption, there's nothing special about negative 0.1. I'll just assume that it's supported on some interval minus m, and okay, it's the right support. So this is my setting. One point that I want to emphasize here is that throughout this part, I am not assuming that the data that I observe is actually drawn from this model. This is not an assumption that I'm making right now. What I am implying by this is that the data as such is given to me, and this is the model that I use to fit the data and to construct the posterior. So this is I'm kind of emphasizing this point because for the third part of the talk, I will shift things, and I will actually assume that things are well specified in that the data actually comes from the model that I fit. But for the moment, this is not something that I need. Yi xi can be thought of as given data. Okay. Any question about the setup for Jiaze? Okay. So I'm interested in understanding, okay, given this setup, I have my log likelihood. I can construct the posterior using the prior and the log likelihood, right? And I want to understand the properties of the posterior distribution. That's sort of my question of interest. I'll focus today on a particular set of, high-dimensional regimes. So I'll let both n and p grow. But for this moment, I'll sort of let p be little o n. So this assumption basically says that p and n are both growing, but the number of features that I have is negligible compared to the number of data points. But one of the assumptions that I'll be making throughout is that, let's say, the operator norm, this is the usual L2 operator norm for my sample covariance matrix, this is always held at some order 1 level, irrespective of the rate at which n and p grow. And I like to think of this essentially as a low SNR kind of regime. So what do I mean by this, and why do I emphasize this point? So the idea in some sense is that, to me, this is sort of one of the challenging regimes because the posterior doesn't quite collapse around a single point. Let me elaborate a bit more on that. So one way to think of this scaling is that, for example, if p is less than n and if the distribution is kind of, if the design is well conditioned, if you think of the usual OLS estimate, then this actually has covariance, which is x transpose x inverse, right? So if x transpose x is some order 1 matrix, then the coordinates of this are non-trivial. So every coordinate has non-trivial fluctuations, and therefore, it's not the case that if there is some data generating truth, your posterior kind of collapses around this point. That's not what is happening, right? The posterior distribution is still quite diffuse. It contains a lot of information about the problem, but it's not kind of becoming degenerate in some way. And this is sort of the regime that I'm interested in for two reasons. One, I think this is sort of really one of the more mathematically challenging regimes where we really don't know what happens to this posterior. And the second, because there is a lot more that is understood in the complementary regime. So in particular, there has been quite a lot of work in in the Bayesian statistics literature where people have tried to understand what happens in high-dimensional regimes, even when p is much bigger than n, but when the operator norm is actually growing. So in these cases, you have this collapsing picture, and things are much better. So I'll restrict myself to this regime as well. Okay, so the question is, I have this high-dimensional posterior. I want to understand its properties. This can help me, do some inference down the line. So how do I understand the properties of the posterior distribution? And here is the idea that I've already kind of mentioned. The idea would be to approximate the posterior distribution by the naive approximation. So the question is, okay, what do I mean really by approximating this posterior by the naive field approximation? What is, how do I talk about the accuracy of this approximation? So the idea here is that if I'm thinking about it, let P be the actual posterior, in my regression problem, right? This is a p-dimensional distribution. And I'm minimizing KL divergence of product measures from this posterior, right? So these are typically two non-degenerate distributions in p dimensions. So typically what will happen is that this infimum will actually be big O of p. If my distribution is actually not really close to any product distribution on mixture products, this is typically what you would expect. And what we'll say is that, this negative mean field approximation is correct to leading order if this infimum is actually little op instead of being big O. So the way to think about this is that you have p dimensions. In general, the way we have scaled things, what would happen is that the scale divergence would be order p because you would have some order 1 contribution coming from each of the dimensions. What I will impose, I will say that this naive mean field approximation is really good if this minimized scale divergence is actually little O of p. The way to interpret that is that somehow you're capturing the leading order behavior, right? Even if there are p independent dimensions, the distribution is close enough to these product distributions such that even though you look at some distributions in p dimensions, you don't get some order p contribution, but you only get those. So of course, this is only a sufficient condition, right? Whenever this is true, this will help us understand the behavior of the posterior. But this is sort of what we have in mind when we say that we will employ this strategy where we'll approximate the posterior by these product distributions. Okay, so this brings us to the next question. When is this a reasonable thing? When is it actually the case that the posterior is kind of approximated by the naive mean field approximation to leading order? So that sort of will bring us to our first main result for GLMs. Now, before I can talk about this result, our result at the moment applies only to certain classes of designs. So let me explain the set of designs to which we can apply the result for a moment. So, okay, for lack of better terminology, I just call these nice designs for the moment. If you have a better term in mind, please let me know. But the idea is the following. So I have n feature vectors, right? And I can form sort of, I look at basically the contribution to the operator norm coming from certain subsets in my data. And what I assume for the moment is that there is one subset of size p which has some order 1 contribution. And then if once you extract that out, if you look at the remaining n minus p feature vectors, the contribution to the operator norm coming from any other set of size p is basically little o1. So I'll give examples to think about things for a moment, but these are essentially the kind of designs to which we can apply the result. Yes?
Sorry, for the first point, is it exists in S or is it?
There exists.
It exists.
Yes. So, okay, maybe I'll give you the punchline so that you can hold on to it till we get to the formal examples. But think of 2 examples. Think of the setting where every row is basically an independent Gaussian with variance 1 over n. In that case, this set S is basically the null set. You don't, if you look at any set of size p, the contribution to the operator norm coming from any such set is basically negligible. I don't have it. So I'll give an example where you actually have these 2 contributions. But this is sort of one example. So I'm not saying that I always need to have this set S. The set S could be null.
So I guess another extreme is the sparse design.
So, okay, so the sparse design, like if you, right. So as we'll see, okay, let me go to the result. The sparse design is definitely, I think, an example of a nice design, but I don't think it will be one where this naive mean field approximation will be correct. So, right. So the result that we have for the moment is that this is a set of sufficient conditions under which the naive mean field approximation will be good for the actual posterior, right? So the first one we've already mentioned. This is sort of this low SNR kind of assumption that my operator norm is always held at a constant level. Our results apply at the moment only to nice designs. But then this is sort of the main assumption that I make, and I'll try to explain this in more detail. So I have conditions essentially on these the sample covariance matrix that you can form out of these two parts. Right? For the part which is of size P and that has order 1 contribution to the operator norm, I assume that the trace of this matrix squared is basically below P. And for the other part, I basically assume that it's similar. You take the matrix, you remove out the diagonal part, and you just look at the off-diagonal part and look at its trace of square. And that has to be little. So if all of these conditions are satisfied, then the naive mean field is correctly modeled. Okay, so what do these assumptions mean? So if you think about it, these matrices, these are all P by P matrices, right? And these have operator norm of order 1. So if you think about it, the trace square in this case is basically the sum of the squared eigenvalues. So I'm looking at the sum of squares of P order, P eigenvalues. If all of them were non-trivial, then this would be big O P. This would be theta of P, right? What I'm requiring here is that instead they have to be little O P. So this is basically saying something like this is an approximately low rank contribution. And then on the other hand, if for the second part, I'm basically putting the same kind of assumption, but here I don't have to look at the entire matrix. I can kind of remove away the diagonals. And this, maybe to give you a taste of what is to come, you can naturally imagine that if my features were all IID Gaussians, then if I was looking at the sample covariance matrix, it would concentrate around the population covariance. So for example, it would be close to identity, right? So if I put this assumption on the entire matrix, it would certainly not hold. But if I remove the diagonals and then assume this consistent. Yes?
And the set S for bullet point 3 is the set from the previous slide?
Yes. So this set S is essentially the part which, of order P many features that has an order 1 contribution. Okay, so let me pause here for a moment to see if there are any questions regarding this.
Maybe go back
Yes,
one more
go
time
back to
this. Is it saying that design is certifiable in some sense, or what is the
what is it saying?
First? Yeah.
Okay, I have a couple of examples. So maybe can I come back to that after I talk about the examples?
Can I ask one thing?
Yes.
Maybe I'm just confused, but I think earlier you said you weren't necessarily assuming that the data was drawn from the actual model.
Yes.
So for this theorem you just showed us, what are we assuming? We're assuming that it actually comes from the model y equals x times beta.
No. All this is saying is that you have your data y and x. If your features satisfy these conditions, then this naive mean field is a good approximation to the posterior. Whether that is kind of, statistically, it tells you how to work with this particular posterior, but it doesn't say, we can of course use these results to say something if we know in addition that the data comes from some model. But at least to me, that's kind of interesting because it allows sort of model mismatch. You have some data, maybe it doesn't come from this exact GLM family, but you can still use this to analyze something.
So y does not even appear in the assumptions, right?
Yes, that's simply because it's
product
linear.
function.
Yeah. Essentially, it's nice. Everything essentially comes down to features. Yes.
What's the relation between the assumption 2 and 3? Or is one of them more strong or weak?
Right. So in some sense, I feel that 2 is kind of the more restricting assumption. It's not that, what I sort of think about is that our result doesn't apply to every kind of design that you can throw at me. It will only apply if the design is nice. But I feel once you restrict, yourself to kind of nice designs. I think the third condition is sort of that in some sense. I can talk more about it. But I feel that if the design is nice, but then like this third condition is violated, then I can give you examples where 9 will not. Okay. So to me, the second assumption is the more restrictive assumption. Okay, so let me comment that this result builds up on a lot of work that has emerged over the past few years in this theory of nonlinear large deviations and its use to analyze sort of models coming from statistical physics and combinatorics. We started with the work of Chatterjee and Dembo, but there's been a lot of work by many people here in this room as well. And there's also work by Ronen and Lan in this area. I should put the references. And I should say that this kind of extends some prior result that Sumit and I had on linear models. So this goes beyond the linear models. Okay, so I think this design niceness assumption is kind of still a bit mysterious. So let me talk about the two examples, right? Okay, here is the first example where you don't have this first block at all, right? This is the case where you actually have a random design setting. So every row that you have is IID coming from some three-dimensional Gaussian with some covariance matrix, gamma of p. And then every feature vector is scaled by 1 over root n. This ensures that your operator norm for the sample covariance matrix is order 1. And so I'm always sort of working in this regime where p is equal to n. In this case, basically, we can kind of approximate in operator norm the sample covariance matrix by the population covariance. So the condition essentially is imposed on the population covariance matrix, right? So this is roughly saying you look at the population covariance matrix, you look at the trace squared of the off-diagonal part of the population covariance. If that is little o p, then the approximation is so in particular, if gamma is identity, this will be that's an extreme. But this is sort of the regime, where I don't have to divide my feature parts into two parts, right? It's S and things not S. So the other example that we've been thinking about quite a lot, I think this was our canonical example in all our discussions, so maybe I'll just write it down. The idea is you have p rows, right? You have n rows. Think of the setting where you have some of these rows that are just 1 over 2. So you have p many rows of this form. And then everything else is like a Gaussian. So xij over root n. Xij is norm on 0. Think of this design, right? If you write down what is the log likelihood in this case, your x beta, so this is your matrix x, the x beta kind of looks a bit strange. It's like you have some beta bar for the first p rows, and then you have this Gaussian, I should call this x tilde. And then you have this x tilde beta. And so it turns out that these two parts essentially behave very differently, right? The first p rows sort of have a very different behavior in terms of posterior, and so we have to kind of deal with it separately. So this sort of leads to this nice design assumption that we say that there's some part that we can extract out where these p rows kind of have an order 1 contribution. And of course, as you can see, this is one example where the result will apply because this first part essentially is low rank. Essentially a rank part. But this is sort of the assumption behind the nice design. Does that answer the question?
Yeah. Besides parts, it seems to suggest separate with this example.
So I'll try to talk more about the sparse design part in the next part of the talk, because I think that's sort of the regime where, like, if it's a true sparse graph, then you really expect that this naive field will not be correct. It's more advanced, like weighted by approximations. So you need to do something more sophisticated. So
maybe I misunderstood Hassan's question, but I thought part of it was that was the verification. Say you have a matrix X, right? Verifying
Right.
assumptions,
Okay.
a priori that's not.
Right. That's a question. Yeah, we thought quite a lot about it. If there is like, if you give me this matrix, if I can give you an algorithm that will immediately tell you whether it's a nice design or not, I don't know the answer to it. We did think a lot about it. We don't have a good answer.
But that sounds should be hard, right?
Should be
because
hard.
it's combinatorial.
Yeah,
It's
we have to
choice.
try all ordered subsets. Yeah, so it would be nice if there was an algorithm to run on the designs.
But is there an algorithm to check whether the naive mean field is accurate? Like if you do the actual optimization and so on, or you can't necessarily know?
No, I don't think you can.
Okay.
Essentially, that's one of the issues. And what is even, maybe to give away some of the message that I'm trying to give off here, as we'll see in the next part of the talk, right? For this IIT Gaussian design case, naive mean field is kind of correct as long as P is little over N. As we'll see in the next part of the talk, P and N are proportional, then it's no longer correct. You need to do something more. But then the issue is, in given some data, you have some fixed P and N, right? Who tells you whether we should consider it P proportional and asymptotic or P? So it's a bit, I think if there were sort of more non-asymptotic results, essentially quantifying how much error is incurred in this would be. But so far, I don't think. Okay. Any other questions on this result? Okay, so what does this buy us? You can say, okay, you've been kind of going on and on about, if the naive mean field approximation is correct, then I understand so much about this posterior distribution. What do you really understand? Right? That's a legitimate question. And I'll try to convince you in the next 2 slides that you actually get quite some information out of this. In particular, one of the first things that one obtains is a leading order approximation to the partition function of this model. And I think I won't have to convince people in this room too much that if you have a control on the partition function, that's a good thing for any high-dimensional distributions, right? So in particular, this partition function is nothing but normalizing constant for this posterior distribution. And so, a couple of lines of algebra actually gives out something very interesting. It basically says that, if the naive mean field approximation is correct in leading order, then it automatically comes with a leading order approximation to the log partition function. Right? So in particular, under this scaling, the log partition function is exactly of order P. On the other hand, we get some approximation which is true to the log partition function up to a little OP correction term. So the way I think about it is that this term essentially captures the leading order behavior for the log partition. Right? But in some sense, this result is sort of non-asymptotic. One of the issues is that the quantity here is still pretty high dimensional, it's field dependent. So whether one can extract more information out of it generally is quite challenging. In some cases, we can. One of the reasons why this sort of variational inference approach has become very popular, I think, especially from the machine learning context, is that it kind of comes with some inferential category. In some sense, it says that here you have some optimization problem, right? This is, if you just look at this quantity by itself, forget whether it's a good approximation to log C or not. This by itself is just an optimization problem. If you can solve it, then it actually gives you the minimizer, one of the minimizers, which minimizes the KL divergence with the posterior. Right? So if you forget everything else, you can just say this gives me a valid estimator for the posterior. I won't work with the true posterior. What I'll try to do is that I'll try to solve this optimization problem over the space of product distributions if I can do it, and if this NMF is correct, then I get a very good proxy for the posterior, and I can do inference. So that has kind of led to a lot of interest in this approach. And that turns out to be quite crucial, even from a theoretical standpoint, which is sort of the next main takeaway that I want to emphasize. I'll be a bit informal here and I'll shove some details under the rug, but if you're interested, I'm happy to elaborate more on this. So in the specific case where, I can take this set S to be the null set. So imagine that all my features are IIT junctions. I don't have the structured part anymore. There's some further simplification that happens. So in particular, one of the theoretical barriers in some sense is that the approximation to the log partition function that I described in the last slide is still an optimization problem over probability distributions, right? So that's quite difficult to handle. Generally, what happens is that you can approximate log z in this specific case by a scalar optimization problem, even though it's a high-dimensional scalar optimization, right? And you should think of this vector u essentially as the mean vector. And in particular, this function m sort of comes with a lot of information about the actual posterior, in that, okay, this function m generally is a non-convex function in high dimensions, but if it has a well-separated optimizer u hat, then this u hat actually helps you understand things like laws of large numbers for samples drawn from the posterior. So what do I mean by this? Let me pause here and talk a bit more about this. So you now have some, in this special case where you don't have the structured part, I'm saying that this optimization problem over the probability distributions can actually be simplified. And it can be simplified to an optimization problem, which is still a high-dimensional optimization problem, but it's a scalar one. At least it's indexed just by this vector. And once that is true, you think of, okay, this is my sketch for this non-convex function in high dimensions. If it has sort of a one good optimizer u hat, then what we can prove is that that u hat essentially governs, or it can help understand laws of large number type behaviors for samples drawn from the posterior distribution. And this is sort of what I have been talking about whenever I say that, oh, if the naive mean field approximation is correct, then I get some information about the actual posterior. So what this is saying is that you draw some sample beta. So beta here is the sample that I draw from the posterior. I look at this empirical average, 1 over p f of some f of beta I. I want to understand the behavior of this empirical average. What this is saying is that there is a law of large numbers type behavior. So this quantity will actually concentrate around a deterministic object. And then this deterministic object is essentially governed by the optimizer to this non-convex.
But beta i's are sampled from pi, not pi hat, right? The left.
So here, this beta I is sampled from the posterior p. So this probability is over the beta I. So beta is a sample drawn from the posterior. I look at this empirical average for a sample that I draw from the posterior distribution, right? I'm saying that, okay, generally this posterior is hard to understand. So I don't know what is the behavior of this average. What I can say is that if there is a well-separated, nice optimizer to hat, then that will help me understand what is the behavior of this. Any questions? Okay, so yes.
But the expectations themselves also should be pretty close, right? So if the left-hand side here was also under expectation. And
yes. So like it depends on the test function now, right? If the test function is kind of bounded, then this is like sort of some convergence probability kind of statement. So if my test function is nice enough, I can state it in terms of expectation.
But you need a nice function for this to be true, probably.
Yes,
well, right?
yes.
So I was just asking that this is concentration about true posterior around the expectation of estimated posterior,
yes.
Right? But then I guess it implies also that the expectation of the true posterior is close to the expectation of the
estimated posterior. Yes. other questions? Okay, so just to summarize what we have said so far. So far what we have looked at, are conditions. These are, I emphasize again, just sufficient conditions for the correctness of this naive mean field approximation. And I've tried to convince you that under certain additional constraints, we can understand, we can extract properties of the posterior out of this naive mean field approximation. Like in particular, we can get this law of large numbers type behavior. And in particular, as I mentioned before, these results, I don't assume that the data actually comes from the model that I fit. They just are results about the posterior distribution. We have some other algorithmic takeaways in terms of what are the classes of optimizing product distributions, but I can talk about it more. Okay, so this brings me to the last part of the talk. So here I'll make all sorts of simplifications because this is a bit more challenging to do. So let's look at just this specific case where the design entries are IID normal 0, 1. Okay. Our earlier results essentially say that if P is little o(n), then the naive mean field approximation is correct. The question is, what can happen if this assumption is not true? Maybe this is just an artifact of our proof and one doesn't really need it, right? What I'll hope to convince you of is that that's not the case. There are other complementary regimes where the naive mean field approximation is expected to be inaccurate. And in particular, okay, so Flora is here. So I found this conjecture in one of their papers, I think, from around 10 years ago. So this is in particular a conjecture about...
But everybody forgot about this one.
I'm reminding everyone. So they have this conjecture about what specifically should happen in this regime of IID Gaussian designs with just a product prior, right? And this is in the context, okay, so specifically this is in the context of the linear models. Forget GLMs, those are very hard for the moment. Come back to linear models, right? So this is supposed to be the approximation for the log partition function. The point here is that if you forget this term in red, then this approximation would look exactly like the one that you had from naive mean field. Okay? This one is basically the expectation of the log likelihood. This one is basically the KL divergence term. The third term that appears, this is purely out of dimensionality effects, and this is often called the tap correction of the Onsager correction term that comes up in this case. Right? And so this is what was conjectured. Okay, so I have some comments about the tap approach, but let me skip this in the interest of time. The question is, what can one prove about this formula, right? So here is a preliminary result that we had a couple of years ago. This is also with Jiaze. So I'm making all these additional assumptions now, and you'll see why I was kind of emphasizing the model freeness of the last part. So first of all, to facilitate computations, I'm going to make my life simpler and I'm going to change the problem. Okay? Instead of working with product priors, I'll work with a uniform spherical prior. So in this case, the vector beta is drawn from the uniform distribution of the sphere in 3 dimensions. I'll also assume that this is a well-specified setting. And by that, I mean that the data actually comes from the linear model where the underlying coefficient beta is drawn from the uniform spherical prior. Right? So I'm going to make all these additional assumptions because at the moment, that's all that we can do. And so so this delta basically represents the noise for the additive Gaussian part in the linear model. So y is x beta plus error. Error has variance delta. So at the moment, we can kind of only prove this representation for delta sufficiently large. That's what we had in our paper. And what we can say is that essentially, we can see why this conjecture is true. So this part sort of is the same. This is the expected log likelihood term that was expected. That comes up. The form for the last part changes, but you can still think of it sort of as the tail divergence term. Its form just changes because we go from a product triad to a cycle triad. But other than that, it's sort of the same thing. And we can see this log correction actually show up. So what is this? Why is it showing up? That's kind of what I hope to talk about.
What is delta again?
Delta is the variance of the additive noise. So you have the linear model y is x beta plus error, and error is Gaussian with variance delta.
Subhabrata, I'm not sure people in the back can see. What's your right? So maybe a little higher.
Yeah.
Maybe here. So y is x beta plus error. Error is normal 0 delta. So that's delta. And in terms of, in a physics sense, this is basically saying that the model is at high enough temperature. This is sort of what we could do at the moment. But this semester, I was teaching a class on some of these topics, and I got some people to think about it. So Kevin is here. Kevin and Bethe are undergrad students here at Harvard. I think they have managed to actually extend this to all possible temperatures. So plugging in there. It's really nice. So what can happen in some sense is that for delta smaller, the form of this correction will change. And they have explicit forms for what we show. But okay, in the last 5 minutes that I have, let me talk about this correction term, how and why you should expect it to show up, what is special about this p proportional to n setting, and what is really going on. So, okay, let me, instead of going through all this notation, let me just draw a picture that's just easy.
I think it's easier to do a picture here for this one.
This
side.
So here you have in some sense you have the posterior distribution living on the surface of the sphere, right? Because this is the posterior under the uniform spherical prior. What essentially is happening is that you essentially look at a band of this form on the surface of the sphere. And essentially, once you recenter the log likelihood around this band, the correction term essentially comes about as the integral of the partition function just over this band. That's sort of the term that shows up. So formally, it's basically just this object. So this is the band, and I'm integrating sort of this log likelihood of Hamiltonian with respect to the uniform spherical. So if you have thought about spin glass sort of models before, you will sort of look at it and recognize this basically as a spherical two-spin model, where the coupling matrix is basically given by the sample covariance. And so this is sort of why you'll see I switched to the uniform spherical prior, because this helps me use sort of random matrix asymptotics to actually evaluate. This is more difficult to do for I don't know how to do it. But at least in this case, if we do it, we get the log correction form. And it turns out that this log correction form is very specifically related to the limiting spectral distribution of the sample. Okay. Okay, there's the upper bound part, which I probably won't get into. I should just comment that we are definitely not the first people to be employing this approach. So a lot of these ideas are coming from advances by Eliran Subag and Weiko Chen and Panchenko and others, improving these stack formulae in the context of mixed spin models. So we're really building up on their showings. Okay, so that sort of is my 1 minute explanation of why the correction term shows up. But there's a bit more to be said about this. The conjecture, in some sense, goes a bit beyond what I mentioned. It's not just a conjecture about the form for the log partition function. Actually, more than that, you expect that this optimizer A So first and foremost, there is expected to be sort of a unique optimizer A. And this optimizer A is expected to have a lot of nice statistical properties. In particular, it is expected that it should lead to Bayes optimal inference. So again, you can say that fine, I can try to prove that this optimization is a good approximation to log Z. I can try to do it. But even if I don't care about it, if I really only want to do inference, I can forget this left-hand side. I can just look at this optimization problem, try to find the best A, and then do inference based on this A. And this is supposed to be really good. And of course, I should say that there is now formal evidence for this in the context of low-rank matrix problems in work by Andrea, Zoe, Michael, Song, Verus, and everyone. So they have these results in the context of low-rank spike matrices, where they prove that if you look at this tap optimization problem, if you optimize it, if you do inference with it, it will give you Bayes optimal inference. And it's actually possible to optimize this landscape efficiently. So the corresponding picture at the moment is missing in the context of linear regression. I think it would be very nice to understand it. You have this problem, can this be optimized? Does this lead to Bayes optimal estimators? And okay, if I forcibly still do the naive mean field solution, I know tap is optimal, but I don't do it. I just do naive mean field. What is the suboptimal in terms of the two solutions? I think these are sort of really interesting things to explore. Let me just finish by saying that my entire discussion today was just focusing on product priors or uniform spherical priors. These are very simple cases. In practice, people use more complicated priors, so I think understanding that would be kind of interesting. The second thing to explore potentially is the fact that typically these approximations are employed in models with latent features and latent variables. We haven't scratched that end yet, and specifically, there's an algorithmic question to this as well, because this workshop also focuses on the algorithmic side of things. So you have this optimization problem, which is potentially non-convex. Can I actually optimize it in practice? How hard is it? And these are some of the references for the papers that I built up. And thanks so much.